So I want to show you now how to add vectors together if they're not pointing in the same direction or opposite. If they're in the same direction, you just add the vectors up. If they're in opposite directions, you do a subtraction to combine them. What if they're not in the same direction? For example, suppose we are hiking and we start right here and we walk 3 miles due east. About right there. Now, that should respect the legend that's given for the map, which is that this distance on the map represents 1 mile. So it should respect the scale of the drawing. So this should be 3. This should be 3 miles. Okay. Suppose we walk 3 miles due east and then 3 miles north. Where do we end up? Well, here's 3 miles east, and I draw 3 miles north, and that puts us about right there. Again, that should respect the scale of the drawing, so this should be 3 miles. So the question is, 3 miles east and 3 miles north, where do we end up compared to where we started? To figure it out, I would now connect the starting point to the end point, like this. And then I would now have to use the scale of the drawing to figure out what this distance is. I would measure it off. Here's about 1 mile, 2 miles, 3 miles, 4 miles, and a little bit more. In fact, it comes out to be about 4.2. So 3 plus 3 doesn't always equal 6. In this case, 3 plus 3 gives us 4.2. So you see, it's a special way to add the vectors together that isn't just adding up the numbers. We use a drawing. You have to do it with a figure. The method that I used here is called the head to tail method. Oh, by the way, of course, this is now kind of obsolete. We could use GPS to figure out what our position is. It's the concept which is important. So this is called the head to tail method. The reason it's called that is because what I have is 3 miles east and 3 miles north, and I have to combine those two vectors together. And what I did was I took one vector, this one, and I put the tip of it and I attached it to the head of the other vector, head to tail, the head of that one onto the tail of the other one. Okay, and it gave me the combined vector, which was here. It doesn't matter what order I add them together. In other words, if I add them in the opposite order, I'll get the same answer. So if I had this, and I have to add them together, I could also add head to tail, but in the opposite order. In other words, I could take this one and put it head to tail. In other words, attach to the head of the other one, and I'd add them up from the start to the end, like so. It gives me exactly the same result. Of course, this is just a sketch. If I really did it right, I would use the scale and everything else and draw perfectly straight lines. But the two two vectors that result from it, doesn't matter what order you add them up in. The vectors that are given in red, this one here, it's called the resultant. So what I've shown you here is a way to add up two vectors, A and B, to get a new vector, which I'm calling C, and C is referred to as the resultant. In other words, it's just the result of adding up the two vectors, A and B. This is the head to tail method. It's the way that I do it when I just want to visualize what the result is. I imagine taking one vector and sliding it over to the head of the other one, head to tail, and then I connect the start to the end. Another way which is useful for drawing out the result is called the parallelogram method. Parallelogram method. So suppose we have to go 3 miles east and 3 miles north. and I want to know where I'm going to end up. In this case, what you do is you draw the two vectors from the same point, and I complete the parallel sides. In other words, I draw a line here, which is parallel to the other vector, and I draw another line which is parallel to this one. So, and in doing so, I complete what's called a parallelogram. It has opposite parallel sides. And when I do that, I can now figure out what the resultant is. Now I connect here. I go across the diagonal of the parallelogram, and that gives me the resultant. So I've done, just in a different method, I've added A and B onto each other, and I found the resultant C. It's just a different way to find A plus B. So we have to use these methods of adding the vectors together whenever we have to add vectors A and B and they're at an angle to each other. They add together to produce the resultant. That's just the result of combining them together using the, in this case, I'll use the parallelogram rule. Of course, you can also use head to tail. So in the notes, you'll find these examples. I urge you to print them out and draw them out on your own to understand what's happening here. Here, I want to add the vectors A and B together. In this case, the parallelogram is given. The side parallel to B is drawn and the side parallel to A is drawn, and you connect across the diagonal to get the resultant. Here, different case, the parallel sides are drawn, I connect across the diagonal. Notice in this one, B is angled upwards, so that means the resultant ends up angling upwards more as well. In picture C, B angles downwards, and now I'm going to draw the resultant in. Again, you should pause it, print, and try it yourself so you get practice with it. So I have to connect across the diagonal from here to there, and there's our resultant, C. Now that B angles downwards, the resultant is more angled downwards as well. And then finally in picture D, I have to draw the parallelogram in. You draw the side parallel to B and the side parallel to A, and then you connect across the diagonal, like so. Remember, all of these drawings should have like a scale to it. So you know that A represents a certain amount and B, and then when you draw the resultant, you can measure off what the amount that it represents. We know that force is a vector. Also, motion is a vector. For example, the hiking example that I just gave, hiking 3 miles east and 3 miles north, that's motion. Motion combines like a vector. Here's another instance of that, a plane. When an airplane flies, doesn't it actually fly upon the air, like gliding upon the air? That means if there's wind, you have to combine the motion of the air with the motion of the plane in the air. It's kind of like walking on a treadmill or walking on a people mover, like at an airport, where I'm walking along, but the belt is carrying me along with it. Same way with an airplane. The plane is moving, but the air that it's moving in itself is in motion. That's what you call wind. So to figure out how a plane actually moves, you have to combine the motion of the wind, the air's motion, onto the motion of the plane. This animation will help us understand what I mean. Here, the plane has an airspeed. In all three cases, the plane has an airspeed of 100 miles per hour, let's say. But on the left-hand picture, there's a tailwind. So the plane's airspeed is 100 miles per hour, but the air itself is moving at 20 miles per hour. That boosts the speed of the plane. And we add the plane's airspeed to the speed of the air itself to figure out how fast the plane goes. It goes faster than it would otherwise. If there's a headwind and the air is actually moving against the plane's airspeed, then you would do a subtraction, and that slows down the plane. If there's a crosswind, then the plane's airspeed is south at 100 miles per hour, but the air itself is moving to the right at 20 miles per hour. Notice how that makes the plane drift sideways. It's still facing south, and it's still heading at 100 miles per hour south, but it's just as an additional sideways motion that's added on. So this is just some motivation as to why we need to learn how to add vectors together to figure out how what the motion is actually going to be. Okay, so here's our examples. All these examples are planes in a crosswind. So let's look at picture A. Here is the air speed of the plane, and here's the speed of the air itself, the wind, pointing off to the right. I need to add them up. I'll add them up using the parallelogram rule. I draw the side parallel. Let's label them like this is A and this is B. I draw the side parallel to A, like so. Make sure you print these out and try them on your own. And then to figure out the resultant, well, I have to draw across the diagonal, like so. So the plane's, in this example, is going to face north, but it'll be drifting sideways as it flies along. In this case, the wind is sort of to the northeast, but the method is the same. I draw the parallel sides. This is A and this is B. I draw the side parallel to A, like that. And then I draw the side parallel to B, like that. And then I'll draw the resultant, which goes across the diagonal, like so. There it is. Notice now the wind somewhat acts like a tailwind, and it actually has a higher speed. Okay, next example, the wind's kind of pointing against it, sort of acting like a headwind. So I'll draw the parallel sides. Draw the parallel side to A, like that. And then I'll draw the side parallel to B, like that. And then I could draw the resultant. There we go. Notice the speed of the plane is smaller than in the other cases. That's because this headwind is slowing it down. Remember that all these figures should have like a scale to them. In other words, 1 inch on this drawing represents, I don't know, 10 miles per hour or whatever. Here's examples with motorboats. The boats, they all have the same water speed, 20 miles per hour or whatever. The difference is that, well, they're in a river, so they have 20 mile per hour speed with respect to the water, but the water itself is in motion. So there are 3 different cases given. In all cases, construct the resultant and show the speed and direction of the boats. So I'll use the parallelogram method in all cases. I draw the side parallel to A. Like so, and I draw the side parallel to B. Like so, and then I connect across the parallelogram from the corner across the diagonal, like so. Next, same thing. Draw the parallelogram. Again, you should try this on your own before I'm doing it, so you have practice. Then I connect across the diagonal. Like that. And then finally, now the boat's kind of headed downstream, and use the parallelogram rule. I draw the side parallel to A. that, and a side parallel to B, like that, and connect across the diagonal. There it is. Okay. Now let's answer the questions. Which boat takes the shortest path to the opposite shore? Well, what I notice in picture A is that the actual motion of the boat is just going to be due east, straight across the river. That's, of course, the shortest possible path across the river is one that takes you directly across. So that's A. Now, which boat reaches the opposite shore first? It's not A, because in A, notice that the boat is not moving that fast to the east. I can compare how fast the boat is moving to the east by looking at these resultants. In picture A, the boat's going 20 miles per hour with respect to the water. But in picture A, the boat has angled itself upstream. And so some of that 20 miles per hour is kind of being wasted just going upriver. In picture B, the boat is pointing itself directly across, and that means the boat is actually going to travel to the east at 20 miles per hour. In picture C, the boat has angled itself somewhat downstream, and that means it will not head east at 20 miles per hour. A and C will not get across as fast as in B. Which boat provides the fastest ride? Well, that's just whichever one has the longest resultant, which is picture C. So previously I showed you how to add two vectors together to get a third vector. In other words, if you're given A and B, you add them up to get the vector C. You add them up using the head to tail rule or the parallelogram rule, and it produces the resultant vector, call it C. Sometimes you know the resultant already, and you need to figure out what two vectors would add together to produce it. So for example, in this figure, suppose I know the vector C already, and I want to know what horizontal and vertical vectors add up to produce it. So we do the parallelogram rule, but let's do it in reverse. So now I already have the resultant, meaning I already know the diagonal across the parallelogram. Therefore, I need to draw the remaining sides of the parallelogram. Here's the horizontal side of it. Horizontal side of the parallelogram right here. And the vertical side of the parallelogram right here. And now I can see the two vectors A and B, which add up to produce that resultant. Here they are. Here's, let's say, the vector A, and here's the vector B. There we go. So that identifies the two, what we call the components of the vector C, A and B. Okay, now they don't have to be horizontal and vertical, but when we talk about components, we mean vectors which are at a right angle to each other. So you see A and B are at a 90-degree angle from each other. And what I figured out is two vectors at a right angle from each other, which produce the resultant C. They don't have to be horizontal and vertical like in the next picture here. Here's the vector C. I'd like to figure out the components which lie along this direction and lie along this direction. Okay, I urge you to pause it and do the parallelogram rule in reverse to figure it out. Okay, welcome back. I'm going to try it myself now. And what I need to do then is draw. I need to work the parallelogram rule in reverse. So first I'll draw the side parallel to this one, which is going to run right about here. Remember, the vector C has to go across the diagonal of the parallelogram. So it's always going to go to the corner of it. That marks the corner of it. So now I'll draw the other side. It has to be parallel to this side now, with its corner right here, like that. There we go. Okay, so I just did the parallelogram rule in reverse. Now I'm going to draw the components. This one, and one more. This one. There we go. So we just figured out the two vectors, A and B, along these two perpendicular directions. They're at a right angle, which will add up to produce the vector C. So for example, you need to pull a giant truck in the direction C with a certain force, but you have these two avenues to pull along. Like it has to be pulled along these two streets. You can pull the truck in this direction using forces that act in this direction and in this direction. They just have to be in exactly the right amount along direction A and along direction B. Okay, let's look at some more examples from the notes here. These first ones, try these on your own. These are drawing the resultants, so the four vectors. So these are A and B, and you add them up yourself to figure out the resultant. Make sure you know how to do that. Next, in reverse, here's the vector C, and I want to figure out the horizontal and the vertical components of that vector. Okay, try the first three on your own, and I'll work out the last one here for practice. So I want to figure out the vertical components of this vector. I'll first draw the vertical direction. Horizontal direction's already there. Now I need to draw the parallelogram. Okay, so I want to draw the horizontal side first. Like so. And now I'll draw the vertical side. Like so. And then I can read off, I'll draw in the two components now. This one and this one. There we go. So we have our two components, A and B, vertical and horizontal parts which add up to produce the vector C. It's just the parallelogram rule, but run in reverse. Now, I've shown you how to draw out the resultant. If you're given a vector A and B, I've just shown you how you can do a scale drawing, so like every inch in the drawing is 1 pound of force or whatever, and draw the resultant using parallelogram or head to tail rule. But if the vectors are just at a right angle, then rather than drawing it out, you can use a mathematical theorem to find the length of the resultant. Okay, so when I add A and B together, I could do head to tail method to draw it. So I'll put A onto the head of B, and then the resultant would be right here, C. The question is, how long is C? You could do a scale drawing to do it, or more efficient to use the Pythagorean theorem. That way, rather than draw a scale drawing, we can just plug into an equation to figure out the length of the vector C. The length of C, you see, C forms the hypotenuse of a right triangle whose sides are A and B. There's a nice right triangle here. And the rule is the length of a right triangle is found by taking A and squaring it, the length of A squared plus the length of B squared, and you add those two and then take the square root of the sum. That's the Pythagorean theorem. Lets us figure out how long the resultant is without measuring it out in a drawing. So for example, a box is pulled north with 60 newtons of force, while it's simultaneously pulled east with 80 newtons of force. So those are the two forces that act on our box, 60 newtons and 80 newtons. And I want to know what's the resultant amount of force If they were in the same direction, you just add them up. If they were in opposite directions, you just subtract them. But if they're at a right angle to each other, then use the Pythagorean theorem to figure it out. Here's the resultant right there, and I'm trying to figure out the length of C. So we'll use Pythagorean theorem. It's given by 60 squared plus 80 squared, and you take the square root of the sum. This is 3600 plus 6400. Take the square root. And then 3600 plus 6400 is just 10,000. So I have the square root of 10,000, which is 100. So you can add 60 and 80 and get 100 if they're at a right angle to each other. There are other ways to simplify. For example, you could factor out a factor of 20 squared from the square root. If you're very familiar with algebra, there are shortcuts. I just worked it out directly. So these vector components, they serve a purpose. For example, here's Nellie. She's pulling a sled. She's actually pulling along the rope, and here's the pull F that she's providing. Now, that force she's giving, it actually has components. Doesn't it have a horizontal part to it? And it also has a vertical part. The horizontal part is what actually pulls the sled along the ground. It's the horizontal part of it, and it gives the horizontal force that pulls it along the ground. The vertical part is actually lifting the sled off the ground slightly and lightening the load and makes it slide more easily. So in this case, the components of the force those two components play their own role in helping her pull the sled along. Okay, let's look at more practice with adding vectors. So this monkey here is hanging by a rope with one arm's holding onto the wall, and there's another force on it, which is the weight of the monkey that's pulling it down towards the earth. In this figure, the weight is indicated with the letters m times g. We'll see later what that means, but it's just the weight of the monkey. Okay, so there are 3 forces on the monkey, and they must all add up to 0. The monkey, I assume, is in equilibrium, so that altogether all the forces are balanced. Now, we know that if I have 20 newtons to the right and 20 newtons to the left, that adds up to 0. But is it possible to have 3 vectors which add up to 0? It sure is. And in fact, let's add up S and T onto each other. T is the rope force. S is the pull from the wall. Adding those two together, and let's see what I get. So I'll use the parallelogram rule. I'll draw the side parallel to S, like so. And then I'm going to draw the side parallel to T, right here. Okay, and then I go across the diagonal to get the resultant, and here it is. That vector right there is the vector S plus T. Okay, notice anything special about S plus T? Well, isn't S plus T just opposite of the weight? And that's how it's possible for the 3 vectors to add up to nothing. S and T together are 2 forces which just exactly balance out the monkey's weight. They have to be arranged that way because the monkey's in equilibrium. It's just hanging out there at rest, and the forces all together have to balance each other out. Okay, let's look at another example. In that case, you see we were given S and T, and I can add them up to see how they cancel the weight. But even if I don't know how big the 2 forces are, I know they have to add to cancel out her weight. So here's Nellie. There are 3 forces acting on her. There's a force S in the left-hand rope and a force T, a tension T, in the right-hand rope. What I know is the 2 tensions together must add up to cancel out her weight, just like how it worked out for the monkey here. Okay, Now, what I know is the tension on the left-hand rope, it acts along the rope. So I should be able to do the parallelogram rule in reverse to figure out what the two tensions S and T are. Okay, there's S and T and there's her weight. Okay, so let's run the parallelogram rule backwards in reverse. So I know that S and T together have to produce this dotted vector because that's going to cancel out her weight. Okay, so I'll draw the side parallel to T like that. Doesn't look too good. Let's try again. Okay, that's better. There we go. And then I'll draw the side parallel to S, like so. So I've just done the parallelogram rule backwards. I'm given the resultant, and now I know that that vector is produced by the sum of this one and this one. That's S, actually, and this one. And that's T. Those two vectors added together produce a force which exactly cancels her weight. So we can see that it's the more vertical rope ends up holding more of her weight, which makes sense. That the more vertical rope, even though it's shorter in length, the length, I should say, the length of the rope itself is shorter, but the length of the rope doesn't determine how strong it's pulling. The pull from the rope is determined by how the components work out. So it's reasonable that, sure, the steeper rope is holding up more of her weight, and we saw how that played out.